So we've talked about single probability events. And for single probability events, we learned that the probability of some event was equal to the desired outcome over all possible outcomes. And we're going to take that concept and stretch it a bit further to talk about geometric probability. So for geometric probability, it's going to deal with area. So in this case, we want to know the probability that it hits a desired area versus the total area. And you have to think that you are shooting randomly at whatever your object is. Or imagine raindrops falling on your object. So if we look at the object in the bottom left, let's say the desired area, the area that I want, is this small square. Okay, it doesn't have to be. It could have been the outside piece. But let's say I wanted this small square. I want to know the probability that some random raindrop is going to land inside my green square and not on my turquoise square. So you have to envision some raindrops falling, and you have to find the ratio of those areas. So how do we do that? We want to find the probability of the green. Well, the desired area then is the area of the green. I'm using subscript green here, so area of the green, over the area of the total shape. And this is a relatively simple problem since they're both squares. So the probability of hitting the green square is the area of the green. Well, the area of the green is a square. We know that the formula for the area of a square is simply the side squared. So here we have 1 by 1 squared. So it's 1 squared over the area of the total. The total shape is the entire large square. So my side lengths are 2 and 2. So it's over 2 squared. 1 squared is simply 1. 2 squared is 4. So my probability of hitting my green square is 1/4, or 25%. What that means is that for every 4 raindrops, 1 of them is going to land in the green area, and the other 3 are going to land outside of the green area. Now we'll move on to a slightly harder problem. These are concentric circles, which means that they share the same center, O. Let's say that this radius is 3, and this radius, the entire thing, is 6. Now, I'm going to do this problem twice. The first time, I'm going to find the probability of hitting the shaded region inside the small circle. The second time, I'm going to find the probability of hitting this donut that is formed by the outside circle minus the inside circle. So this donut is either called a donut, a ring, or an annulus. You'll see those problems a lot. So for the first problem over here, I want the probability of the red. So it's equal to the area desired. So it's the area of the small circle. I'm going to say FC, area of the small circle, over the area total. Well, the area of the total is simply the big circle in this case. So I'm just going to say the area of the big circle. We know that the formula for a circle, area of a circle, is pi r squared. So if we're going to just simply plug that in here. So the probability of hitting my red, the small circle, is pi r squared for the small circle. My radius for the small is 3. So 3 squared over pi r squared again. My radius for the big circle is 6. So 6 squared. We can simplify that a little bit. Pi over pi are going to cancel. We get 3 squared is 9. And 6 squared is 36. 9 over 36, we can reduce that. and it becomes 1/4. Now that's just a coincidence that I had 1/4 again. So we'll hold on to that for a second. Now let's go over to look at the green one. This one's a little bit more difficult. The probability that's going to hit the green part, the ring, is the area of the ring. Now the area of the ring is a little bit tricky to find out. The area of the ring is going to be the entire circle minus the part that's punched out, the part that's missing. So to find the area of the ring, it's going to be the area of the big circle minus the part that's missing, which is the small circle, so minus the area of the small circle. We're going to put that over the area of the total. Well, the area of the total is still the big circle, and that hasn't changed. Now we can actually just use my numbers from the left side of the problem over here. So the probability of the green is equal to area of the big circle. We knew that that was pi 6 squared minus area of the small circle. Well, the area of the small circle is pi 3 squared over the area of the big circle, which was pi 6 squared again. We can clean this up a little bit. The pi's are going to cancel. And so we're going to get the probability of the green is 36 minus 9 over 36. That's going to equal 27 over 36. And we can reduce that a little bit more, and it's going to be 3/4. So the odds that it hits the red are 1/4 or 25%. The odd that it hits the green is 3/4 or 75%. And what I want you to notice here is if you have 25% and 75%, you're going to get 100%. That makes sense if we're looking at the pictures, because if we talk about the small circle and the outer ring together, that's the entire shape. So it has to either hit the red part or the green part. So together it's going to be 100%. Another problem. This is an inscribed circle. That means it's drawn inside of a square. And here they haven't given us any numbers. And this is where you need to use variables. So as with all circles, it's going to be helpful to draw a radius. And we're going to call that r. Let's say that I want to find the probability of hitting this circle. Probability of hitting this circle. Now we're going to solve for this in terms of r, and we'll see what happens. Well, we know that the probability of hitting the circle is equal to the area desired, which is the circle, so the area of the circle, over the area total. Well, my total area here is a square, so it's the area of the square. Now, we know that the area of the circle is simply pi r squared. That's the formula you learned a long time ago. The area of the square, then, is the side times the side, but we need to find out what one side is going to be. Well, we know that this is the radius, but we also know that that radius has to go to the other side. So together, this is 2r. That 2r, then, is the same as one side length of your square. So this side must also be 2r. So the area of my square, then, has to be 2r times 2r. And we can simplify a little bit. We get pi r squared over 2 times 2 is 4, and we get r squared. Now what's nice about this problem is that even though I gave you no numbers, and we only did it in terms of r, those r's are going to cancel. We have an r squared over an r squared. Those are going to cancel each other out. And my final probability is simply going to be pi over 4. So the probability that it hits the circle is going to be pi over 4. the reason we did this problem is to show you that we don't need to have the numbers in order to solve it. Now let's make this one step harder. Let's say I wanted to find the probability of hitting these corners. So these blue corners I'm shading in. So the probability of blue. Well, we could easily redo the problem. We could subtract off the circle just like we did for the last problem. But we're going to use a hint that we learned together, or learned last problem. We know that together the entire shape has to be 100%. And if we express 100% as a number, we know that together it has to be 1. So we know that the odds of hitting the circle are pi over 4. That's what we computed earlier. So the leftover then is the blue part. So if together it has to equal 100%, which we can express as 1, the odds that it hits the blue part are simply going to be 1 minus pi over 4. So here we took the total, we subtracted off the probability that it hits the red circle, and we found whatever was left. Well, that turned out to be exactly what we wanted. So the total minus the red circle gave us exactly what we wanted. So the probability is right there. Simply 1 minus pi over 4. I'll leave you with this challenge problem that you can work together on as a class. Find the probability of hitting the square inside the circle. So once again, there's no numbers. This is going to be a slightly harder problem. And hopefully if you get stuck, your teacher can guide you through it. But you're going to have to come up with a place to draw the radius, find the area of your circle, and find the area of your square in order to solve this problem. Best of luck.